Okay friends, we will start with our next practical of integrator circuitry. So we will be using LM356 IC because this has got high slew rate of 12 volt per microsecond. And let us see first the design steps for the integrator circuitry. So here you can see this is a basic integrator circuitry. We are using CF and R1. I know for our practical the problem statement is we have to design a practical integrator with the frequency 1.5 kilohertz, gain equal to 10, and we are assuming feedback capacitor is equal to 0.01 microfarad. So using this data, we know the integrator formula for the cutoff frequency FA and FB. We know the gain formula. So in this, if you substitute FA is equal to 1.5K and CF is equal to 0.01, we obtain RF is equal to 10 kilo-ohm. Similarly, we will get R1 value equal to 1K. So with these design values, we are building a practical integrator. Now in the practical integrator, we are having the additional feedback, that is the RF. We know the drawback of the integrator circuitry at a DC voltage or at the low frequency, this CF, that is the XC value, becomes infinite, so it will be an open loop configuration. So to get the integration at low frequency also, we are using this feedback resistor, and this circuit is known as practical integrator. So for the practical now, what you have to do, we need to plot the frequency response, and here you can see we will be changing the input frequency in the steps of 100 Hz, 1K, then 10K up to 15K. You will be monitoring the output voltage of your circuit. You are converting, you will be calculating the gain, that is equal to output upon input. Input is equal to 1 volt peak to peak. So whatever the gain you are getting, that is converted into dB gain. Okay, and then we are plotting the frequency response. So I will show you the standard frequency response over here. So here on the x-axis we have frequency, on the y-axis this is your gain in dB. So at up to FA, you can see here we are getting the constant amplitude, and after FA it drops, and when this magnitude plot cuts 0 dB line, that is known as your FB frequency. So up to FA your circuit acts as an inverting amplifier, and after that between FA to FB your circuit acts as an integrator. Now let us see the response on the DSO. Now on the DSO, first I will give you the sine wave. So here you can see input is the sine wave, the first channel is connected to your function generator, and this is the output of your integrator circuitry. Now here you can see peak to peak voltage for channel 1 is 1 volt, and we can measure the peak to peak output voltage of channel 2 as well. So here you can see it is 1.48 volt. Now if I change the frequency, I will start with the auto set. Yeah, so this is your input frequency, this is your output waveform, and you can measure the channel 2 output voltage. So peak to peak voltage is 10 volt. And now if you see the relation between this input and output, so simply I will just overlap both the waveforms, and you can observe now frequency is only 100 Hz. So here you can see that only you are getting the inverted sign at the output. So if your frequency is less than FA, so for example I have kept 100 Hz, I am getting inverted sine wave. Now if I change the frequency, and which will more than FA, so let me change the frequency. Okay, for example I have kept the frequency equal to something 12 kilohertz. Okay, and again I will just adjust the waveform. We know the integration of sine is minus cosine waveform. Okay, so here you are getting the minus cosine waveform. So likewise you have to change the input frequency, and you have to observe the output waveform. So this is for the integrator. Stop. That's better.